Hey everybody, this is the lecture on section 5.3, which is on diagonalization. So given an n by n matrix A with eigenvalues k1, k2, kn, not necessarily distinct. Suppose that there exists linearly independent vectors right, that is, a basis for R in V1 to Vn, where Vi is an eigenvector for eigenvalue Ki. Okay, so you've got these eigenvalues, and you always have n eigenvalues, possibly with repetitions, because the characteristic polynomial of the matrix is a polynomial of degree n, which has n roots, up to multiplicities. And suppose that you have, for those eigenvalues, corresponding eigenvectors that are linearly independent. This doesn't have to happen. Okay, this need not exist, but, sometimes it does. Not this, but these don't have to exist. All right, in this case, let P be the n by n matrix whose columns are V1 to Vn. Let P be the, this matrix, and therefore, and let P be equal to this, and D be equal to the following matrix. So it's the matrix that has the eigenvalues along the diagonal and is 0 everywhere else. Okay, so P is this matrix whose columns are the eigenvectors for these eigenvalues, which are the entries on D, a diagonal matrix. Okay? Now, A times P is equal to A times, this matrix whose columns are the eigenvectors, V1 to Vn. And the matrix product is, the matrix whose columns are AV1 to AVn. But each of these is an eigenvector with eigenvalue k1, k2, up to kn. So AV1 is kV1. AVN is, k1 v1, and AVN is kn vn. Also, so A times P is equal to this. Also, P times D, what does that equal to? That is V1 Vn times this diagonal matrix over here. Let me copy that. And when you work out this product, what do you get? You get exactly this right here. Right? You're going to have the column, the first column, right? So first row, first column is K1 times the first entry in V1, and then zeros everywhere else. First column, second row is, well, first column, any row, right? You're going to take just K1, 0, 0, 0, 0, 0, and multiply by V1 and then other things. So you're just going to get that the first column is K1, V1, and that the last column is Kn, Vn. But this is equal to AP. Right? So, right, PD is equal to AP, and since the columns of matrix P were assumed to be linearly independent, we therefore get that P inverse exists. So, what does that get us? So, PD equal to AP yields P inverse PD equal to P inverse AP. Well, P times P inverse cancel, and you get D is equal to P inverse AP. And this is a very desirable identity for various reasons, but sort of the most immediate reason is the following. So this is useful for calculating the exponent a to the n. Or sorry, a to the power n, right, which is equal to a times a times a times a n times. Right, I mean, how many arithmetic operations are there in doing a matrix multiplication? When you have n rows and n columns, and you have to multiply every row by every column and add those products up, right? So you do that n squared times. So that's a lot of multiplication that's going on there. However, right, since ordinary matrix multiplication takes a lot of arithmetic, well, not since, but ordinary matrix multiplication requires a lot of arithmetic. Okay, however, right, d to the n, because d is diagonal, All right, this is K1, K2, all the way up to Kn with zeros everywhere else. That doesn't take hardly any arithmetic at all. That's just K1 to the n, K2 to the n, I shouldn't use the same exponent, should I? A to the R, no, R, A to the M, N, O, P, A to the M times, so this is M, there we go. So K1 to the M, K2 to the M, Kn to the N. All right, which doesn't require any matrix multiplication at all. Now, D to the M is equal to P inverse AP to the M is equal to, well, so D is P inverse AP. So that's P inverse AP, P inverse AP, P inverse AP. And you keep going like that. P inverse AP. And all of these things cancel. And what you get is P inverse A to the M, P. Right? So, A to the M is equal to P D to the M P inverse, which requires only two matrix products rather than M matrix products. Right, so that's like a computation saving device. Now there's other things you can do with that other than this, but that's sort of the most immediate benefit that you get. And calculating powers of matrices is important when you're doing, like in particular, like stochastic analysis. Give me a moment, I'll be back. Okay, so let's summarize what we have so far. So the diagonalization process is as follows. Okay, step one, find the eigenvalues for matrix A. Step two, find a basis for the eigenspace of each eigenvalue. Step three, if you get, so we'll say this is an n by n matrix N. If, and you don't have to, you obtain n vectors total in part 2, then P will be equal to the matrix whose columns are these eigenvectors and D is the diagonal matrix with eigenvalues placed in the corresponding columns for each eigenvector. Right, so like if the first column in P has eigenvalue 2, then the first column of D should have on its diagonal 2. If the next column is eigenvalue -3 in P, second column is eigenvalue 3, then the second column in D should have the 3 in it. And you know, when we obtain n vectors in step 2, right, you find a basis for the eigenspace of each eigenvalue. And then if you obtain n vectors in total in part 2, right, you know for the distinct eigenvalues that the eigenvectors are linearly independent. So it's just within non-distinct eigenvalues. You know, if you can get more than one eigenvector that's linearly independent, you know, especially for those eigenvalues that have, in particular for those eigenvalues that have multiplicity greater than 1, you know, then you'll be guaranteed to obtain linearly independent vectors in total. Now, you won't necessarily get all n vectors, but, you know, if you can't, then you can't diagonalize. If you can, then you can. And then P is just the matrix whose columns are those eigenvectors, and D is the diagonal matrix of the eigenvalues along the diagonal. So, for example, let's see. So let A be equal to 1, 1, 2, minus 1, minus 1. No, sorry. 3, 1, 2, minus 1, 1, negative 2, and 2, 2, 6. Find a matrix P, diagonal matrix D, and invertible matrix P, such that D equals P inverse AP. Okay? So, here we go. First thing you got to do is find the eigenvalues. All right, so you got to calculate the characteristic polynomial. So this is step 1. All right, well, the characteristic polynomial is the determinant of this matrix here, 1 minus k minus 2, 2, 2, 6 minus k. Right, that was the matrix A minus IK. Or, yeah, A minus KI. Right, so we're trying to calculate the determinant A minus KI. So that's this matrix here. Now you have to use the 1 minus K, 2. Use the, you know, a cofactor type expansion, or for 3 by 3 matrices you can do this. You can't really do it too easily with row reductions. So here we go. This is going to be 3 minus k 1 minus k, 6 minus k, and then 1, negative 2, 2, minus 4, and then 2, negative 1, 2, minus 4, minus 4 times 1 minus k, and then plus 4 times 3 minus k, right? 2 times 1 minus k, minus 4 times 3 minus k, and then plus 6 minus k. Alright, so this is equal to, so the product of these two is 3 minus k minus 4k plus k squared times 6 minus k minus 8 minus 4 plus 4k plus 12 minus 4k plus 6 minus k. So those cancel, and then minus 12 plus 12. So just left with a 6 minus k there. So this is equal to 6 minus k times 3 minus 4k plus k squared plus 1. So this is 6 minus k times 4 minus 4k plus k squared. So this is equal to 6 minus k and then 2 minus k squared. Yes, this is 2 minus k squared. So eigenvalues are given by 6 minus k, 2 minus k squared equal to 0, so you get k equal to 2 and 6. All right, so we have two eigenvalues. K is positive 2 and k is 6. All right, so that's the end of step 1. Step 2, look at the eigenspace for each eigenvalue. So we'll start with k equal to 6. All right, so A was what? Right here. All right, so this is A minus 6I is this minus 600,060,006. All right, which is 3 minus 6 is minus 3, 1, 2. 1 minus 6 is minus 7. And 2, 2, 0. Yes. Okay, so I'm going to move this up to the top and divide it by 2. So I got 1, 1, 0. 1, 7, well, minus 1, minus 7, minus 2, minus 3, 1, 2. All right, and add this to second row. 0, minus 6, minus 2. Add it 3 times here. 0, 1, 1 plus 3 is 4, 2. So something isn't right. Did I copy that down? Did I copy that? This is minus 5 here. 1 minus, no, it's positive 1 minus 6 is minus 5, so that's minus 5. So this is minus 4. There we go. So you should always get an eigenvector for each eigenvalue, so you're going to get a row of zeros here somehow. Adding this stuff together, you get 1, 1, 0, the row 2 and row 3, 0, 1, 1 half, 0, 0, 0. And then subtracting actually I'm going to leave it as 2, 1. And then, no, I guess 1, 1 half. Subtracting this from here, you get 1, 0, negative 1 half, 0, 1, 1 half, 0, 0, 0. So x3 is free, x2 is minus a half, x3, and x1 is 1 half, x3. So I have x1, x2, x3 equal to x3 times 1 half, negative 1 half, 1. Okay, so I could pick this as the eigenvector, so I'm going to double it. So pick eigenvector 1, negative 1, 2. I'll just multiply it by 2. All of these, anything in the eigenspace is already an eigenvector. So I mean, I can pick x3 to be 1, or I can pick x3 to be 2 and pick that eigenvector. So there we go. 1 minus 1. It's not linearly independent from this, of course. You can't get more than 1. That's linearly independent. Okay. Next, a minus 2i So we have 2's along the diagonal here. So 3 minus 2, 1, 1, 2, minus 2, negative 1, negative 1, negative 2, and then 2, 2, 6. And then all row 1, it cancels out both rows. Alright, so x2 and x3 are free. And x1 is minus 2x minus x2 minus 2x3. So we have that x1, x2, x3 is equal to minus x2 minus 2x3, x2, x3. So this is equal to x2 times minus 1, 1, 0. Plus x3 times minus 2, 0, 1. So pick eigenvectors minus 1, 1, 0 and minus 2, 0, 1. So let D equal, so step 3, let D equal the diagonal matrix 6, 2, 2 along the diagonal, and let P be equal to, so the eigenvalue for the 6 is 1, negative 1, 2. Right, that's eigenvalue for the 6. So the 6 goes in the first column. right? Eigenvector for 6, eigenvalue for 6. And then eigenvectors for 2, minus 1, 1, 0, and minus 2, 0, 1. And we know that D is equal to P inverse AP. And that's it. So we'll go over a lot more examples like this during the lecture, but that's, or during the problem session, but that's all in section 5.3.